Welcome to Stellar Stories, where we dare to explore the universe's most mind-bending secrets. Today, prepare to have your reality warped as we reveal the top 10 utterly bizarre facts about space. We're talking white holes, cosmic earthquakes, and colossal clouds of pure alcohol drifting through the cosmos. If you're ready to question everything you thought you knew, stay tuned. As a tiny channel, your support means the universe to me. Please like and subscribe if you enjoy what you see. And because I'm small, I can personally respond to your comments. Let's dive into the cosmic abyss. Imagine an earthquake, but not on Earth. We're talking about a star so dense, a single teaspoon of its material would weigh billions of tons. These are neutron stars, the ultra-compact remnants of massive stellar explosions. And they shake. These aren't your garden variety tremors. They're starquakes, or more accurately, neutron star quakes. The immense gravitational and magnetic forces at play cause the star's crust, a super dense layer of neutrons, to crack and shift violently. And when I say violently, I mean violently. These quakes release energy comparable to our sun's entire century of output, all in a matter of seconds. They cause the star to wobble, emitting powerful bursts of X-rays that can be detected light years away. Think about it, a tremor on a star so powerful it can reshape its surface and send out shockwaves of energy across the cosmos. It's a reminder that even in the most extreme environments, change happens, and it happens with a force we can barely comprehend. And that's just the start of the cosmic weirdness. Next up, we're venturing into a place so empty, it'll make you feel agoraphobic. Cosmic emptiness, the void that swallows light. Now, if you thought a starquake was unsettling, how about a place where, there's almost nothing? I'm talking about the Boötes Void, also known as the Great Nothing. It's a colossal spherical region of space, roughly 330 million light-years in diameter, located in the constellation Boötes. Discovered in 1981 by astronomer Robert Kirshner and his team during a survey of galaxy redshifts, the void was initially a puzzle. They expected to find hundreds, if not thousands, of galaxies within this space. Instead, they found almost nothing. To date, only about 60 galaxies have been identified within the void, a stark contrast to the thousands that should statistically exist in a region of that size. Imagine this, if the Milky Way were smack dab in the center of the Boötes Void, we wouldn't have known about other galaxies until the 1960s, because they'd be so incredibly far away. That's how mind-bogglingly empty it is. Now, how does something like this even happen? That's where things get speculative. The leading theory is that the Boötes Void was formed by the merger of smaller voids. Imagine soap bubbles coalescing into one giant bubble, pushing the galaxies to the edges. But even this theory has its limitations. It doesn't fully explain the sheer scale of the emptiness. Some more out there ideas have been proposed. One involves the possibility of a cosmic string, a hypothetical, one-dimensional topological defect in space-time, slicing through the region and sweeping it clean. Others suggest it could be the result of advanced alien civilizations, perhaps using the region as a vast, isolated construction zone, or even as a buffer between galactic empires. And then there's the truly wild speculation. What if the Boötes Void is a pocket universe? A region where the laws of physics are slightly different, a bubble of reality within our own. Or even more bizarre, what if it's a remnant of a previous universe, a scar left behind from a cosmic collision? We simply don't know for sure. The Boötes Void stands as a stark reminder of how little we truly understand about the universe. It's a cosmic mystery, a vast, silent emptiness that challenges our very notions of space and time. And it begs the question, what else is out there, lurking in the shadows of the cosmos, waiting to be discovered? Now let's shift our focus to something equally mysterious, but instead of pushing galaxies away, it's pulling them in. I'm talking about the Great Attractor. Imagine our Milky Way galaxy, along with millions of other galaxies, all being drawn towards a specific point in space. It's like a cosmic whirlpool, a gravitational behemoth that's exerting an immense influence across hundreds of millions of light years. This unseen force is what we call the Great Attractor. The Great Attractor was first theorized in the 1970s, as astronomers noticed that the motion of our local galaxy supercluster, the Laniakea supercluster, couldn't be explained by the gravitational pull of visible matter alone. There had to be something else, something massive, hidden behind the obscuring dust and gas of our own Milky Way's galactic plane. So what is it? That's the million light-year question. We know it's incredibly massive, possibly containing the equivalent of tens of thousands of Milky Way-sized galaxies. But what form does it take? One of the leading theories is that it's a massive concentration of galaxies, a supercluster far larger and denser than anything we've observed so far. But this supercluster would have to be incredibly dense and contain an extraordinary amount of dark matter. Dark matter, that mysterious substance that makes up about 85% of all matter in the universe, could be the key to the Great Attractor's immense gravitational pull. But there are other, more speculative ideas. Some scientists have proposed that it could be a wall of galaxies, an immense structure stretching across vast distances, pulling galaxies towards it like a cosmic conveyor belt. And then, there are the truly mind-bending theories. What if the Great Attractor isn't made of matter at all? What if it's a tension in space-time itself, a region where the fabric of the universe is warped and twisted, pulling everything towards it? Or, even more bizarre, what if it's a gateway to another dimension, a portal through which galaxies are being drawn into an unknown realm? The truth is, we don't know. The Great Attractor remains hidden, obscured by the zone of avoidance, a region of the sky blocked by our own galaxy. To peer behind this veil, we need to use advanced techniques like X-ray, astronomy, and radio telescopes, capable of penetrating the dust and gas. The Great Attractor is a cosmic enigma, a silent puppeteer pulling on the strings of galaxies across vast distances. It's a reminder that even in our vast and detailed maps of the universe, there are still hidden giants, unseen forces shaping the cosmos in ways we're only beginning to understand. Now let's shrink our scale and explore something downright bizarre. Exoplanets, where water exists as hot ice. Forget everything you know about ice. When we say hot ice, we're not talking about frozen water at sub-zero temperatures. We're talking about a solid form of water that exists at incredibly high temperatures and pressures, conditions that would instantly vaporize water on Earth. These exoplanets, often massive and gaseous, like Neptune or Uranus on steroids, possess atmospheres with crushing pressures. Under these extreme conditions, water molecules are forced into a crystalline structure, forming a solid that's denser than liquid water. Think about it. A planet with a surface temperature of hundreds of degrees Celsius, yet it's covered in ice. It's a paradox, a state of matter that defies our everyday experience. This hot ice, also known as Ice 7, is a testament to the sheer diversity of physical phenomena that can exist in the universe. The existence of hot ice was initially theorized, but recent research has provided compelling evidence that it's not just a theoretical concept. Scientists have used sophisticated computer simulations and laboratory experiments to replicate the extreme conditions found on these exoplanets, confirming that water can indeed solidify into this exotic form. But what does it mean for the possibility of life? Well, that's where things get really speculative. While hot ice itself is unlikely to support life as we know it, the extreme pressures and temperatures could create unique chemical reactions and environments. Perhaps, deep within the layers of these planets, beneath the hot ice crust, there could be regions where liquid water exists, warmed by the planet's internal heat. Or perhaps, life on these planets would be so radically different from our own that it would be unrecognizable. Imagine organisms that thrive in extreme pressures, utilizing the unique chemical properties of hot ice to survive. The discovery of hot ice exoplanets challenges our Earth-centric view of habitability. It forces us to reconsider the range of environments where life could potentially exist. It's a reminder that the universe is full of surprises and that our understanding of physics and chemistry is constantly evolving. And who knows, perhaps one day we'll discover an exoplanet where hot ice isn't just a curiosity, but a crucial component of a truly alien ecosystem. Imagine a world untethered, a planet adrift in the vast cosmic ocean, unburdened by the gravity of a star. These are rogue planets, celestial nomads wandering the interstellar void. Unlike their star-orbiting cousins, rogue planets have been ejected from their parent solar systems, perhaps through gravitational slingshots during chaotic planetary formation or stellar close encounters. They are wanderers, traversing the immense gulfs between stars, bathed not in starlight, but in the faint glow of distant galaxies. The existence of rogue planets is no longer just a theoretical concept. Astronomers have detected objects that appear to fit the description, though confirming their rogue status can be challenging. But if they're out there, and evidence suggests they are, then their implications are mind-boggling. Let's get speculative. What would life be like on a world without a sun? It would be a realm of perpetual darkness, a frozen wasteland on the surface, but perhaps not entirely. Internal heat, generated by the planet's core or through tidal forces from interactions with large moons, could create subsurface oceans. Imagine vast, liquid water seas hidden beneath thick layers of ice, warmed by geothermal vents. These oceans could be teeming with life, chemosynthetic ecosystems thriving in the absence of sunlight, similar to the deep-sea hydrothermal vents on Earth. But let's push the boundaries even further. What if some rogue planets have incredibly dense atmospheres, trapping the faint background radiation of the universe, creating a habitable, albeit dim, environment? Could life evolve in such conditions, perhaps with unique adaptations to perceive and utilize this faint energy? And here's a truly wild thought. What if rogue planets act as cosmic arcs? Perhaps they could carry life from one star system to another, seeding the galaxy with life's building blocks, or even with fully evolved organisms. This concept, known as panspermia, takes on a whole new dimension when considering rogue planets. Imagine a rogue planet hurtling through space for billions of years, a frozen time capsule carrying within it a unique biosphere. It could eventually be captured by another star system, thawing out and giving rise to a completely alien form of life, shaped by the unique conditions of its long interstellar journey. The possibilities are endless, and the challenges are immense. Detecting and studying rogue planets is incredibly difficult. They're dark, faint, and hard to distinguish from other cosmic objects. But as our technology improves and our understanding of the universe deepens, we may one day unlock the secrets of these nomadic worlds. Rogue planets represent the ultimate frontier of exploration, a testament to the resilience and adaptability of life, and a reminder that the universe is far stranger and more wondrous than we can currently imagine. We've all heard of black holes, the cosmic vacuum cleaners that devour everything in their path. But what if there were their opposite? What if there were regions of space-time that, instead of consuming, violently eject matter and light, enter white holes? The concept of white holes arises from the mathematics of Einstein's field equations, the same equations that predict black holes. They are, in essence, time-reversed black holes. While a black hole has an event horizon that nothing can escape, a white hole has an event horizon that nothing can enter. Imagine a cosmic geyser erupting with unimaginable force, spewing out matter and energy that has been trapped for eons. It's a truly mind-boggling idea, a region of space where the arrow of time seems to run in reverse. Now, the evidence for white holes is, well, non-existent. We've never observed one directly. They remain purely theoretical objects, mathematical curiosities. But that hasn't stopped scientists from speculating about their potential role in the universe. One of the most intriguing possibilities is their connection to the Big Bang. What if our universe wasn't born from a singularity, a point of infinite density, but from the eruption of a colossal white hole from another universe? Imagine our cosmos as the ejected debris from a cosmic sneeze, the remnants of a previous universe's demise. Another theory proposes that white holes could be the other side of black holes, connected by wormholes, theoretical tunnels through space-time. Imagine matter falling into a black hole in one universe and then being ejected from a white hole in another, potentially in a completely different time or location. And then there's the truly wild speculation: what if white holes are the engines powering quasars, those incredibly powerful explosions that light up the universe? Quasars are known to eject vast jets of matter and energy, sometimes at speeds close to the speed of light. The sheer amount of energy involved is staggering, requiring massive engines at their cores. Supermassive black holes are the currently favoured explanation, with their accretion disks and relativistic jets. But what if there's another possibility? Imagine a white hole, not consuming, but violently ejecting matter and energy. This ejection wouldn't be a steady flow, but potentially a chaotic, eruptive process, explaining the variability seen in quasar emissions. The immense energy released by a white hole could easily power the observed luminosity of these objects. Furthermore, the jets observed from quasars often appear to be highly collimated, meaning they're focused into narrow beams. While black holes can produce collimated jets, a white hole, by its very nature, would be ejecting matter in a focused direction. Now, why would this be a compelling, albeit speculative, alternative? Well, it could help explain some of the mysteries surrounding quasars that are still difficult to reconcile with purely black hole-based models. For example, some quasars show variability in their emissions on timescales that are shorter than the light crossing time of their central black hole, which is hard to explain. A white hole, with its potentially more chaotic and eruptive nature, might offer a solution, and if quasars were powered by white holes, it would suggest a fundamental symmetry in the universe, with black holes and white holes acting as opposing forces, shaping the evolution of galaxies. This would also imply an interconnectedness of regions of space-time that we currently don't understand. The truth is, we don't know. White holes remain a cosmic enigma, a tantalizing possibility that challenges our understanding of space and time. But they also represent the boundless creativity of the universe, a reminder that even the most outlandish ideas might one day be proven true. When we look up at the cosmos, we tend to think of gravity as the ultimate architect, shaping galaxies, stars, and planets. But what if there's another force at play, one that's equally, if not more, influential on the grandest scales? What if the universe is fundamentally electric? This is the core idea behind the plasma universe theory. Now, this theory stands in stark contrast to the standard cosmological model, which relies heavily on gravity and dark matter. The plasma universe proposes that electromagnetism, specifically the behavior of plasma, the fourth state of matter, plays a dominant role in shaping the cosmos. Plasma, an ionized gas containing free electrons and ions, makes up the vast majority of visible matter in the universe. Stars, nebulae, and even the interstellar medium are primarily composed of plasma. And plasma, unlike neutral gas, is highly conductive, allowing electric currents and magnetic fields to propagate over vast distances. The plasma universe theory suggests that these electric currents, flowing along vast cosmic filaments, can create powerful magnetic fields that shape galaxies and even galaxy clusters. Imagine galaxies not as gravitationally bound structures, but as nodes in a cosmic circuit connected by immense Birkeland currents, named after the Norwegian physicist Christian Birkeland. These currents, according to the theory, can pinch and twist plasma, forming stars and galaxies. They can also explain the observed rotation curves of galaxies without the need for dark matter, as the electromagnetic forces can provide the necessary centripetal acceleration, and the implications go even further. The theory proposes that the cosmic microwave background radiation, often cited as evidence for the Big Bang, could instead be the result of energy released from these vast cosmic currents. The redshifting of light from distant galaxies, another pillar of the Big Bang model, could be explained by plasma interactions rather than the expansion of space. Now it's crucial to understand that the plasma universe theory is highly controversial. It's not widely accepted within the mainstream scientific community. It faces significant challenges, particularly in explaining certain cosmological observations that the standard model addresses more effectively. But that doesn't mean it's without merit. The theory has its proponents, who point to laboratory experiments and astrophysical observations that seem to support its claims. They argue that the standard model relies too heavily on hypothetical entities like dark matter and dark energy, while the plasma universe offers a more direct, observation-based approach. Regardless of its ultimate validity, the plasma universe theory serves as a valuable reminder that our understanding of the cosmos is constantly evolving. It challenges us to question our assumptions and to explore alternative explanations. And who knows, perhaps one day we'll discover that the universe is far more electric than we ever imagined. We tend to think of life as we know it, carbon-based, water-dependent, and reliant on DNA. But what if life on other planets has taken a completely different path? What if there are shadow biospheres, alien ecosystems that are utterly unrecognizable to us? The concept of shadow biospheres explores the possibility that life can arise using alternative biochemistries, fundamentally different from our own. Imagine life forms that don't rely on carbon, but on silicon or other elements, or life that doesn't use water as a solvent, but perhaps methane or liquid nitrogen. The possibilities are endless. We know that many elements can form complex molecules, and that a wide range of solvents can support chemical reactions. So, why should life be limited to the specific combination we see on Earth? One intriguing possibility is life based on alternative genetic materials. DNA and RNA are incredibly efficient, but they're not the only molecules capable of storing and transmitting genetic information. Perhaps alien life uses peptide nucleic acids, PNAs, or threose nucleic acids, TNAs, or even completely unknown molecules. Or perhaps alien life doesn't even use molecules at all. What if it's based on plasma structures or on patterns of energy flow? These forms of life would be so different from our own that we might not even recognize them as life. The implications of shadow biospheres are profound. If they exist, it would mean that life is far more common in the universe than we currently believe. It would expand the search for extraterrestrial life beyond the narrow confines of Earth-like planets. But how would we detect them? That's the challenge. Traditional methods of searching for biosignatures, like looking for oxygen or methane in a planet's atmosphere, wouldn't work. We would need to develop new techniques, perhaps by searching for unusual chemical imbalances or unexpected energy patterns. And what if these shadow biospheres are right under our noses? What if they exist on Earth, in extreme environments that we haven't fully explored? The deep subsurface, the high-pressure environments of the ocean trenches, or even the clouds of Venus, could harbour life that's completely different from what we know. The search for shadow biospheres is a humbling reminder that our understanding of life is limited by our own experience. It's a call to expand our horizons, to think beyond the familiar, and to embrace the truly alien. And who knows, perhaps one day we'll discover that life is far more diverse and adaptable than we ever imagined, existing in forms that challenge our very definition of what it means to be alive. We're used to crystals, those orderly arrangements of atoms that repeat in space. But what if there were crystals that repeat in time? Enter time crystals. Time crystals are a theoretical phase of matter, a bizarre state where the structure repeats not in space, but in time. Imagine a crystal that oscillates, changing its state in a periodic fashion, even in its ground state, without requiring any external energy input. It's a perpetual motion machine, but not in the classical sense, violating time translation symmetry instead. This concept, initially proposed by Nobel laureate Frank Wilczek, challenges our fundamental understanding of equilibrium and symmetry. In a typical crystal, atoms arrange themselves in a repeating spatial pattern to minimize their energy. But time crystals break this rule, exhibiting a repeating pattern in time, a rhythmic oscillation that persists indefinitely. Now, time crystals have been created in laboratories, albeit in highly controlled environments. But what if they exist naturally in the extreme environments of space? Imagine time crystals forming in the incredibly dense cores of neutron stars, where gravity and pressure are so immense that they warp our understanding of physics. Or what if they exist near black holes, where space-time itself is twisted and distorted, creating conditions that allow for the formation of these exotic structures? The implications are mind-boggling. Time crystals could potentially warp our understanding of time itself. They could allow us to probe the fundamental nature of space-time, to explore the boundaries of physics as we know it. And then there's the truly wild speculation: what if time crystals are the key to understanding dark energy, the mysterious force that's accelerating the expansion of the universe? Perhaps dark energy isn't a force at all, but a manifestation of time crystals on a cosmic scale, a rhythmic oscillation of space-time itself. Or what if time crystals are the building blocks of wormholes, theoretical tunnels through space-time? Imagine using time crystals to stabilize wormholes, allowing for faster-than-light travel, or even time travel. Imagine the cosmos as a colossal brain, a vast neural network stretching across billions of light years. Some scientists and philosophers are exploring the possibility that the universe might function as a form of computational system, and that the distribution of galaxies and cosmic structures could resemble a giant neural network. The large-scale structure of the universe, with its filaments, clusters, and voids, bears a striking resemblance to the architecture of neural networks, the computational systems that power artificial intelligence. Just as neurons in a brain are connected by synapses, galaxies in the universe appear to be connected by filaments of dark matter and gas. These filaments form what we might interpret as a cosmic web, a vast network of interconnected nodes, where galaxies could be seen as processing units, and the flow of matter and energy as information transfer. Now, let's consider the idea that this cosmic network might be capable of learning and evolving. Perhaps the universe is constantly processing information, adapting to its environment, and possibly even developing a form of emergent intelligence. Dark matter could be the wiring of this cosmic brain, the unseen connections that allow information to flow across vast distances. Galaxies, with their complex structures and interactions, might be interpreted as the neurons, processing information and generating outputs. And what about the voids, those vast empty regions of space? Perhaps they're not empty at all, but rather the memory banks of the universe, storing information in the form of quantum fluctuations or other exotic phenomena. This concept raises some fascinating questions. Could the universe be processing information? Is it possible it's simulating the laws of physics, or even creating new realities? And what about consciousness? Could the universe itself exhibit some form of emergent awareness, a vast, distributed intelligence that transcends our current understanding? Some theorists have even proposed that our own consciousness might be a microcosm of this cosmic intelligence, a neural network within a neural network. Perhaps our brains are tiny nodes in the universe's grand computational system, each contributing to the overall processing power. And here's a truly mind-bending idea. Could the universe be constantly simulating itself, creating nested simulations within simulations, like a cosmic Mandelbrot set? Perhaps our reality is just one layer in this vast, infinite hierarchy of simulations. The implications are potentially staggering. If the universe were a neural network, it would revolutionize our understanding of physics, cosmology, and even consciousness. It might blur the lines between information, matter, and energy, suggesting that they are all fundamentally interconnected. It's important to remember that this is a highly speculative idea, but it's this kind of radical thinking that pushes the boundaries of our knowledge. By exploring even the most outlandish possibilities, we might stumble upon a deeper understanding of the universe and our place within it. And who knows, perhaps one day we'll discover that the cosmos is far more complex and interconnected than we currently imagine. Imagine a bar, not on Earth, but in the vast expanse of the Milky Way. A bar where the drinks are measured in light years and the atmosphere is a swirling cocktail of cosmic chemicals. You might be surprised to learn this isn't just a fantasy. There are, in fact, vast clouds of alcohol floating in interstellar space. Specifically, we're talking about molecular clouds, regions of space where dust and gas coalesce, forming the nurseries of stars, and within these clouds, complex organic molecules, including alcohols, are brewing. Take Sagittarius B2, for example. This giant molecular cloud, located near the center of our galaxy, is a veritable cosmic distillery. It contains billions upon billions of liters of alcohol, primarily methanol, the poisonous kind, but also traces of ethanol, the kind you'd find in your favorite drink. Now don't pack your space suitcase just yet. This cosmic booze isn't exactly ready for consumption. It's spread out over such a vast area that it's incredibly dilute. But the sheer quantity of it is staggering. Imagine the ultimate party with enough alcohol to fill countless trillions of pints. And it's not just alcohol. Sagittarius B2 also contains other fascinating molecules, like ethyl formate, which gives raspberries their distinctive flavor and rum its characteristic smell. It's a complex chemical soup, a testament to the rich and diverse chemistry that occurs in the interstellar medium. How does this cosmic cocktail come to be? It's a result of chemical reactions taking place on the surfaces of dust grains, tiny particles of rock and ice that float through space. These grains act as catalysts, facilitating the formation of complex organic molecules. The discovery of these alcohol clouds isn't just a curiosity. It provides valuable insights into the formation of organic molecules, the building blocks of life in the universe. It shows us that even in the seemingly barren emptiness of space, complex chemistry is at work, creating a cosmic brew that's as intoxicating as it is intriguing. So the next time you raise a glass, remember, you're sharing a drink with the cosmos. Cheers, and thanks for watching Stellar Stories. See you next time.